Hi students, today we're going to learn about further integration. Okay, this topic has got 6 learning outcomes. We will learn about how to integrate certain polynomial functions that will actually result in trigonometric functions. And we will also look at standard integrals. The second learning outcome will discuss how to integrate rational functions. The learning outcome will actually focus on the technique of integration called integration by parts. The fourth learning outcome, I will introduce to you what is differential equations. And the fifth learning outcome will actually discuss how to apply some of the techniques to actually integrate using the variable separable method. And the sixth learning outcome will be application of all the differential equations that you integrated earlier. The first learning outcome will look into standard integrals. As you are aware, if dy dx is known as antiderivative and say dy dx equals to x, and the indefinite integral, when you integrate your dy dx with respect to x, you will actually get your fx. You need to remember all the integral identities which you have learned from semester 1 or equivalent to higher maths. So these are the standard integrals, which are example ax to the power of n. When you integrate, you will actually arrive to this. So for example, if you integrate 5x to the power of 3, you will get 5x to the power of 4 over 4 plus c. And for example, if you integrate cosine ax plus b, your resultant will be 1 over a. Integrate cos will give you sine ax plus b. And don't forget the c, because this is simply an indefinite integral. And when you integrate sine ax plus b with respect to x, your resultant will be negative 1 over a cosine ax plus b. And of course, don't forget your c, because this is an indefinite integral. From the differentiation exercise for the past 2 weeks, you are aware that e to the power, when you differentiate e to the power of x, you actually get ex, e to the power of x. When you differentiate ln x, is 1 over x. When you, an example, if you differentiate tangent, is secant square. So therefore, the antiderivative here will be integrating e to the power of x will actually result in ex, and integrating 1 to the power of x will actually give you ln x. Integrating secant square will actually give you tangent. And of course, the c is added because these are indefinite integrals. Indefinite integrals meaning integral without limits. Just take note that over here ln x is modulus, so therefore you only consider the positive values of it. Okay, ln. Now we will look into some examples where the 3 previous formulas are actually applied. So example, if you need to integrate e to the power of 3x and e to the power of 3x with this two particular limit. So example, integrating 0 to 1 e power 3x plus 1 to 2, you can actually summarize this between 0 and 2, and this can be shortened into only integrating e to the power of 3x once between 0 and 2. So the limit 1 and 1 gets cancelled out here. So next, you just integrating this gives you e to the power of 3x over 3, because this is integration. And then you just substitute 2 and minus substitute x as 0, and you will arrive to this answer. For the second example, when you need to integrate 5 over x with respect to x, is as if you are integrating 5 multiplied by 1 over x. So as we looked into the previous slide, Integrating 1 over x gives you ln x. So your final answer will be 5 ln x plus c. And you can bring the 5 up as the index can also be the power of c. Now we will look at the third example. It requires you to actually integrate tangent square. And you're aware that there is no formula to integrate tangent square, so there is a modification required whenever we want to integrate something involving trigonometric functions. You can use trigonometric identities to integrate what is possible. So for example, um, this is deriving, yeah, we know that we can write tangent square in terms of secant square. So this is derived from the basic using sine square cos plus cos square equals to 1. So we divide the whole equation here with cosine square, sine square over cos square over cos square, and 1 over cos square. So this will reduce to tangent square x plus 1 equals a secant square. And we are aware of this identity. And this identity is also provided in the formula list for the exam. So you don't need to derive here. I'm just showing you as a form of knowledge, yeah. So when you can't integrate tangent square, but you know that you can actually integrate secant square, so you can use this identity to get tangent square as secant square x minus 1, right? So instead of integrating tangent square, you can actually integrate secant square x minus 1, and the final result will still be the same. So integrating secant square, we know it gives us tangent x. Okay, so when you integrate this term, you will actually arrive to tangent x. So integrating secant square x gives you tangent x. Integrating minus 1 gives you minus x. And of course, don't forget the c. Now we will look into how to integrate polynomial terms that will actually result in inverse trigonometric functions. So for example, if you integrate 1 over 1 minus x squared, it will actually give you sine negative 1x plus c. Because when we differentiate sine negative 1x, it will actually give us 1 over sine of 1 minus x squared. So this is using the concept of anti-differentiation, yeah. So next, if you need, so looking further, if this x is not only x, so example, if you have integration with respect to x, a square minus x square, therefore your resultant will be sine negative 1 x over a plus c. So you have to actually write it or modify a term in terms of a square minus x square, set of a square minus x square. So we'll look at example in the coming slides. So same goes for inverse tangent. Recap back, when you actually differentiate inverse tangent x, your result will be 1 over 1 plus x squared. So when you integrate 1 over 1 plus x squared, it will be result of an anti-differentiation, which is inverse tangent x. So if your a is not 1, so you need to do some modification. You need to write in terms of integration of 1 over a squared plus x squared. Your resultant will be 1 over a inverse tangent x over a plus c. Same goes for cosine formula. It's just that cosine formula actually has a negative added to it. Okay. Hi. Now we will actually look into the next example where we need to actually integrate 1 over set of 9 minus x squared. So this is very clearly related to the previous slide, where it is 3 square minus x square third. So this is obviously the resultant is the inverse sine x over a, and the a here is 3 square here. So the a is 3, right? And then the limit stays the same, 3 and 1.5. So you substitute 3 over 3 result to 1 minus substitute x as 1.5. And then next, this will be your final answer. Inverse sine, so please pay attention. When you do the calculation, make sure this is in radian mode, yeah. And this is your final answer, which is pi over 3. Now we will look at the second example, which is evaluate integration of 0 to 1 for 1 over 2 plus x squared. This is clearly similar to integrating 1 over 1 plus x squared, which always gives you inverse tangent. So next, you have to be careful with your calculation. The formula for inverse integration of 1 over 1 plus x squared, it gives you 1 over, you have to match this to a square plus x square. So a square here becomes, you just set 2 square gives you 2 again. So it's 1 over a, which is set 2, plus, multiply by inverse tangent x over a. The a is set 2. Because 2 here is equivalent to a square, so it has to be set 2 square. So your a is set 2. And you maintain the limits. Next, you just substitute accordingly. Substitute x as 1. Get this first part, minus substitute x as 0 for the second part. And then please be reminded to convert your mode of calculator to radians so that you leave your final answer in terms of pi. Now we will look into the third example, which is evaluate. There are no limits, so it's an indefinite integral. 1 over 3 minus 4x squared. So this question is slightly different because you have a coefficient in front of the x squared. I'm very sure that by now you know the resultant will be an inverse sine. Okay, so what we need to do here is we need to get rid, the first step is we need to get rid of the coefficient of x squared. So in order to get rid of the coefficient of x squared here, which is 4, we bring out 4 as a common factor. So if we bring out 4, then you have to make the 3 over 4, so that when you multiply in back, it actually goes back to the question, which is 3 minus 4x squared. So this is the modification required. First step, get rid of the coefficient of x squared. Next step, try to bring the value out. So set of 4 is actually 2 and you bring the 2 out. Okay, the next step is this 2 is 1 over 2, so you can bring it out here. You can write it outside of the integral sign. And this part here, you write it in terms of a square minus x square. So it's easier for you to fit it into the inverse sine formula. So the half is this, integrate, dx stays. So 3 over 4, writing in terms of a square is actually set of 3 over 4. So set of 3 over 4 is set 3 over 2 because set of 4 is actually 2. So a is set 3 over 2 minus x squared. So next, you actually match it to the formula of inverse sine. So it becomes, the half is from here. You just bring it down. So integrating 1 over a squared minus x squared is inverse sine x over a. So your a is set 3 over 2. And of course, you have to add plus c because this is an indefinite integral. So your final answer, you can rearrange it properly, and x over a over b, it will be, the 2 will go up. Okay, so half inverse sine 2x over 3 plus c will be your final answer for this question.